Hi, everyone. My name is Grace Pratt, and I'm a policy analyst with the California Energy Storage Alliance. Really want to welcome you all to this spotlight webinar that is really talking about AC versus DC coupled energy storage, as well as the use and considerations of the different types of coupling, particularly in microgrids. So for those that are familiar with CESA, you'll know that we really like webinars that tackle subjects that we all want to learn more about. And I'm really excited to dive into what is a pretty technical topic, but one that is important. And I think that the fundamental question behind this topic is, how do we extract as much value as possible from our coupled generation and energy storage resources? And in particular, how do we think about this in the microgrid space, which is really where we're trying to serve load with a more limited set of resources than what we might be dealing with in the larger grid. And I'm really excited to be joined by my co-panelists today. So without further ado, I will let them introduce themselves. Michael, did you want to kick us off?
Sure. So I'm Michael Worry, CEO and CTO of Nuvation Energy. Joined here by Maximo.
Yes, hi, Michael. Hi, everyone. I'm Maximo Torres, CEO of Maximo Solar Industries and Sunbit Energy. So I'm very pleased to be here and share our experience with DC coupling.
Yeah, and I already gave a brief introduction, but I'm Grace Pratt. I'm a policy and legislative analyst on the CESA team. And to get started, we did want to learn a little bit more about all of you here in the audience with a few poll questions. So I'll launch the first one. So the first one is asking whether your organization works directly on solar and/or storage projects. And I have a feeling I know which will be the most popular answer for this one. Okay, I'll give folks about 5 more seconds. Okay. So no surprise there. Most of you do work directly on these projects, which is great to hear. I hope that you'll find this session really valuable. And then for our next question, will you be developing a new market solution or working on a project within the next 6 months? Okay. And it looks like that is a resounding yes. So it's really great to hear that there are a lot of folks in the audience that are active in this space. But even if you're not as active, I still think that this will be a really interesting session, and we really hope that you learn a lot. So our agenda is pretty jam-packed, but I'm going to kick us off really talking about the California market for microgrids, why microgrids are deployed in California, some of the challenges that we're facing in the state. I'll then pass it off to Nuvation to really dive into the nitty-gritty on AC versus DC coupling. And there is going to be a bunch of detail on the actual power conversions, the architecture, and all of the engineering work. And then Nuvation and Maximo will be sharing a project example. And then we'll wrap up with Q&A. So we really do welcome participation and questions, and we would love to answer your questions. If you do have questions, please type them into the Q&A box. We won't be answering questions during the session. Instead, we'll really be reserving those for the end, but please feel free to drop a question in at any time. So with that, I just wanted to start off with a little introduction for those that don't know the California Energy Storage Alliance, or CESA. So we are the definitive voice of storage here in the state. We're really working to grow all aspects of the market, whether that be in front of the meter, behind the meter, short duration, long duration, all of the above in California through our advocacy at the state legislature, our state agencies, and also other relevant policymakers, whether that be at the local or federal level. And our work would not be possible without our wonderful members. CESA has over 120 members now. So I know that there are CESA members in the audience here today. Thank you all for joining and thank you for your support. So diving right into microgrids, I think the most important question to start with is, what is a microgrid? So there are a lot of different definitions of microgrids offered by different codes and standards bodies, but California actually does have a microgrid definition in statute. So SB 1339 defined a microgrid as an interconnected system of loads and energy resources that are specifically designed to meet customer needs. These microgrids should have a clearly defined electrical boundary and can be run as a single controllable entity that can connect to, disconnect from, or run in parallel with the larger electrical grid. These can also be managed and isolated to withstand larger disturbances and maintain electrical supply if the larger grid does have an outage. And I like to think of two different types of microgrids. The first is a customer facility or a single user microgrid. These are microgrids that are really serving just one entity or electrical customer. You might hear these called behind the meter microgrids because the generation, storage, or other distributed energy resources are being installed on the customer site behind the utility meter, and electricity doesn't need to be carried by utility wires. These can be pretty simple, but they can also be more complex. We do have larger customers such as university campuses or military bases that are one customer, but that do have multiple buildings and loads that can be controlled in a microgrid. The second type of microgrid is a community microgrid. These are really those microgrids that are more complex because they're serving multiple electric customers. They can use a combination of in front of the meter and behind the meter resources, and they can use utility wires to distribute electricity to and between customers when the system's islanded. And while less common, we are seeing deployment of multi-customer or community microgrids, and we have a few deployed in the state today. So this leads us to why people want microgrids at all. I'd say that largely microgrid adoption in California has really been driven by a desire for resiliency or the ability to maintain power when the larger grid has an outage. And in California in particular, some of the most common causes of outages are wildfire related. Public safety power shutoffs and enhanced power line safety settings are both measures taken by utilities to proactively de-energize lines. This is done in order to prevent utility equipment causing fires, but outages are also caused by the wildfires themselves or other extreme weather events. So this is a really big driver because customers are looking for how they can have a reliable electric supply during these outages. But microgrids can also provide other benefits, including electric bill savings, time of use arbitrage, and demand charge management, the same as other behind the meter systems. And also customers or businesses can have their own clean energy goals, and having their own renewable generation storage really reduces their use of electricity from the grid. And even though California has made a lot of progress in cleaning up the grid, we still have about 50% of our electricity coming from natural gas. So while microgrid deployment has increased, there are still barriers. Cost remains a major barrier for many. And in response, California has created some incentive programs to help offset costs. The first is a self-generation incentive program. This is a really long-standing program that has taken many forms, but has supported the deployment of behind-the-meter storage for a while now. However, funding has run low in the program. We may see additional funding added next year. There have been a lot of talks. The governor has a proposal to add more funding, but this will likely be really focused on the residential sector. On the multi-customer side, the Microgrid Incentive Program has been created to help support those types of projects in disadvantaged and vulnerable communities, but we haven't seen the program launch yet. And then lastly, just to leave you with some more of the technical and policy barriers as well, one of the technical barriers that's faced is that the microgrid isolation technologies, those technologies that really allow you to island from the larger grid, are more approved by the utilities on an ad hoc basis at the moment, instead of having a uniform approval process. That would be more easy for technology providers to follow. This has been hampering the ability for industry to really deploy solutions quickly. And then on the regulatory side, multi-customer microgrids don't have access to a microgrid tariff. This is currently being developed at the Public Utilities Commission, but we have seen delays on that end as well. And so this is still a barrier that's being faced by many. So I hope that was a helpful introduction to microgrids in California and some of the opportunities and challenges. And with that, I will pass it off to Michael.
Great, thanks, Grace. So I'll start with a little bit of an introduction of who Nuvation is. So next slide speaks to who we are as a company. And so Nuvation got started in 1997, 25 years ago. And actually, I recently learned that Maximo also got founded in 1997. So we're both celebrating our 25th year anniversaries this year. Our roots are as an electronic product design company. And so we've done a wide variety of projects over the years, obviously lots of energy storage, but also electric vehicles, industrial controls, medical devices, defense and aerospace, many different things. In 2008, we founded Nuvation Energy, and that's really the focus of what we're speaking about today. I'm based out of our Silicon Valley, California office, and we also have an office in Waterloo, Ontario, Canada. Over our 25 years of operation, we've designed and delivered over 1,000 products and projects into market. Next slide. So let's talk about Nuvation Energy and what we do as a company. So the roots of the company are inside of our battery management system, and this is a functionally recognized UL 1973 system that provides for both small and large energy storage applications. Above that, we have our energy management system, and we'll be speaking about both of those today. And then we offer a suite of engineering services, all of this being done for organizations that are developing and deploying energy storage systems. Next slide. This gives a little bit more detail inside of our energy storage services and what that looks like. So companies often hire us in order to design full turnkey energy storage systems. It'll start with the research phase where we can look at what batteries are the best choice for a particular application, as well as selecting the power conversion system. We can design as needed the modules and racks and containers for particular applications. We can also do full custom site controller development. Many of these applications are existing legacy designs where they have particular equipment already on site that one should integrate with, and we can manage all of that. We also have full support to manage certification for our customers. So we've done that for a number of our customers. We're managing the UL process, such as UL 1973, and all the certifications related to that. We do the thermal management, and all this rolls up into data logging and analytics, which can both be locally as well as up in the cloud. Next slide. With that, we'll dive in a little bit into AC coupled and DC coupled systems. So let's kind of like start with like a definition of what that looks like. So on the left-hand side here, we've got a typical AC coupled system. Bottom left, we've got the point of interconnect, which is your grid, and obviously an AC grid. The first column there, you've got a solar array going through solar optimizers, through a solar inverter. That's a one-way energy, putting energy onto the AC bus. Beside that, we've got storage. So we've got batteries protected by a battery management system, going through a bidirectional battery inverter, because it can both charge and discharge the battery, connecting onto the AC grid. And beside that, we've got an electric vehicle going through an EV charge controller. Typically, that's pulling energy from the AC bus and charging the electric vehicle. If it's a vehicle to grid application, that can also be bidirectional. So that's called an AC coupled system because all of the different sources of energy and loads all connect together on the AC bus. On the right-hand side of this diagram, we've got a DC coupled system. So you can see that it's the same sources and loads, solar array, battery, and electric vehicle, but now all of those are connected on the DC side. So you've got a solar charge controller hooked to the DC bus, the EV charge controller is a DC-DC converter, and the batteries and BMS are hooked directly. You've then got one single power conversion equipment that does the AC to DC to AC conversion, and that of course then is bidirectional. So that just kind of defines the terms of what we're talking about today between AC coupled and DC coupled. Next slide, please. So let's talk about when AC coupled systems make sense. So a good example of that is if you're adding storage to an existing solar installation, AC coupling is often the least disruptive because you've already got a bunch of equipment on site, and then you can add on an AC coupled solution. Another example is if a site has high peak loads on the AC bus, then adding an AC coupling system can enable further AC capabilities because you're aggregating the AC power of both the solar and the storage in order to service that higher load. And then the largest reason as to why AC coupling is used is because it is the most common installed option. And so there's just more options of components and equipment that are out there, as well as more domain knowledge doing AC coupled solutions. Next slide. So to describe the other side of that as to when DC coupling makes sense. If you're designing a new solar plus storage system with DC coupling, you've got opportunity to have higher efficiency when storing energy because there's less energy conversions. If you keep everything in the DC domain, then you save the efficiency losses of doing the DC-AC conversions multiple times. There's also opportunity to have a reduction in the overall device and component count. We're going to give some examples of that. And then if you're in certain situations where, for example, you're using income tax credits and you want the ability to get the income tax credit on the storage side of the system, there are sometimes rules that you can only charge that storage using solar energy. And so in a DC coupled system, you can enforce charging at a configuration level to do that only from solar. If you're in an AC coupled system, you can absolutely still do that. You then add an energy management system such as Nuvation's N controller in order to manage the control loop around that. Another advantage of DC coupling systems is you can do whatever you like on the DC bus without being worried about that impacting the grid interconnection. Sometimes the grid interconnection can have complicated permits and so forth around it. So doing things on the DC side avoid the need in order to manage that. You can, for example, add DC fast charging onto an existing DC coupled system and do that without potentially increasing the grid interconnection. DC fast charging can have a significant impact in the power draw from the grid, and so it can be advantage to do that on the DC coupling side. Next slide, please. So now let's get into power conversion and the different things around that. Next slide. So these are examples of the kinds of equipment that we'll use in string optimizers, charge controllers, DC-DC converters. These are the types of equipment that show up inside of DC coupled systems. Next to their solar array, you're going to have what's called a maximum power point tracker. And a solar panel has a voltage current curve that comes out of it. And a MPPT floats around that voltage and current in order to find the point where you can draw the maximum power out of that solar panel. That then goes to a DC-DC converter either to convert it onto a TC bus or in an AC coupled system, you'd have a DC-AC to couple that onto an AC bus. Next slide. So this shows examples of DC-AC conversion. So on the left-hand side here, we've kind of got a traditional AC coupled system where you've got solar with optimizer and a solar inverter. Commonly in applications nowadays, that solar optimizer or MPPT is combined with the solar inverter. So it's a single piece of equipment. And then you've got your battery, BMS, and battery inverter. On the right-hand side, what we wanted to highlight here is that there's a number of applications today where you can find hybrid inverters, which are a good match for the application. And then you have a single piece of power equipment that includes your MPPT, your solar charge controller, as well as your bidirectional battery inverter. So the advantage of that is you have a single piece of equipment that manages all that for you. Potential disadvantage is that you're then you have the fixed ratios of power that's available for that particular solar array and power battery bandwidth. Next slide. So this we also wanted to talk about round trip efficiency, and so here we're doing a comparison between the round trip efficiency of a DC coupled system and an AC coupled system. So you can see in this top example, we've got a solar array, a DC-DC converter. That DC bus then flows over the top of the battery, goes DC to AC out to the grid. And so in this application, if you want to charge the battery, it's only going through one DC-DC converter in order to match to the stack voltage of the battery. And so you get a round trip efficiency of about 96%. The lower example is a traditional AC coupled approach, and you can see how you go through solar panels, a DC to AC converter, potentially go through a pair of transformers, go back AC to DC conversion and back into the battery. So obviously there's more conversions that occur here, and so it results in a net lower efficiency. So we're down in a round trip efficiency more like 93%. So the net of this is that delivery of energy without storage will always be more efficient in a DC coupled solution, and that's what we wanted to show here. Next slide. So let's talk a bit about microgrid architecture. So as Grace introduced at the start, often a lot of the applications that we do are microgrid based. And so when you get into an application where you're doing a number of things with the system, you want an energy management system. This here is an example of some screenshots from Nuvation's end controller, which is our energy management system. And this can do things such as PV smoothing. So if you have a grid, a solar array, and a cloud passes over and you've got a sudden loss in power, you want the EMS to step in and discharge the battery in order to smooth out the slew rate of the power. Or if you're doing, for example, demand charge management, you want the EMS in order to be monitoring the AC meters on the load side. And if you get an increase, a peak in the amount of power being drawn, we want the EMS to come in there and ask the battery to discharge in order to shave that peak. So in net of all that, the EMS is making the decisions as to when to charge or discharge the batteries based on what energy application is being used on this site. In this particular graphic, you can see this is one of our sites in the field. So it's monitoring solar power, it's monitoring the battery. You can see here it has both the energy available as well as the storage available. And this is one of the cool parts of having a battery in a microgrid system is it's got a dual nature, is it can provide both the ability to provide energy similar to a generator or a solar array, but it can also provide the ability to be a load and absorb energy. And so it's got that cool dual nature. We of course track the load and the grid connection. This particular application had 5 battery packs and 5 PCSs, and so the end controller EMS is managing all of that. Next slide, please. This shows a few of the graphs that are available inside of the system. And so you can track graphically solar generation, load, discharging from the battery. And so you can see, for example, where you get these like orange peaks and it's doing more discharge in the battery. that results in the lower graph here, where the state of charge of the battery is decreasing. This lower graph actually shows the duality of both the available energy and the available storage. The storage graph is inverted so that the lines are correlated, and that shows you how those are linked together. When EMS is making decisions, it's going to be pulling data from a lot of different equipment that's on the site. So for example, the battery management system is providing information on the battery, such as state of charge, as well as your charge and discharge current limits. It'll also be pulling information from your solar array and how much power is coming out of the solar array. You'll be talking with power meters to get data on the AC meters of your loads, as well as the configuration of, what schedule are we loaded here, what energy application is being used here. Next slide. We wanted to speak a little bit about that on the DC coupling side. There's a variety of different ways this can be done. And so the left-hand side is a DC coupled solar and storage option, where the solar array has with it both the optimizers as well as the solar charge controllers in a single unit. And so it has the intelligence to know how to pull power out of the solar array, as well as how to charge a battery. And that's arguably the most efficient way in order to do a DC coupled system. We can compare that to what we have on the right-hand side here. And in this case, there's a battery charge controller that's added in order to manage the charging and discharging the batteries. This is a more common architecture when it's an existing solar system and you're adding storage to that. This may came up in applications, for example, like the recent Inflation Reduction Act, where now we can go back and add storage to existing solar arrays. So these kinds of architectures often come out of that. You do need to be careful in applications like this to make sure that the battery is not backfeeding into the solar array. So just checking that the solar equipment on site ensures that that won't happen. Next slide, please. We also wanted to talk about backup power and how AC coupled and DC coupled can be different in those sort of applications. So this is a block diagram showing an AC coupled system of solar plus storage with backup power. And so you can see on the bottom left there, we've got our three-phase AC power. You've got that yellow box of non-backed up loads, and that's followed by a contactor which provides with islanding capability. So in the event of loss of grid power, that islanding contactor opens, and you're still left with your green backed up loads being provided for out of the solar array and the battery that we have behind the system. All of this is controlled by the site controller, which is our Nuvation Energy controller EMS. That has a local hardware on the site in order to run the energy application. It also rolls up into our Nuvation Energy cloud services that provides additional storage, visibility remotely as to what's going on in the system, remote authentication and configuration options, as well as more advanced algorithms that can be run with a cloud level of data and processing. Let's compare that on the next slide. We have a DC coupled solar plus storage with backup power, and we can see there that it's the same loads and same equipment for generation. However, there's like less orange boxes, which is your components that are doing power conversion and so forth. And so similar architecture. But the battery and the solar array are now DC coupled and hooked together on the DC bus. So there's just a single solar inverter to battery inverter doing that DC AC conversion. To roll that up to do a component comparison, we do that on the next slide. And this kind of shows a table of the components that are involved in a AC coupled to DC coupled. So as we highlighted at the start, one of the advantages of a DC coupled system, it has less total components. So on the solar optimizers and charge controllers, let's say we have an N number of those depending on the size of the solar array. Both cases we have a solar DC to AC, but the storage DC to AC is only required on the AC coupled side. We don't need that for the DC coupled. DC coupled also saves an additional AC meter. So the net of that is an AC coupled solution is N plus 6 in terms of its component, whereas a DC coupled is less than that, N plus 4. And so there's less components in the system, which can contribute to reducing overall system cost. So that's the comparison we wanted to show. With that, next slide, I'll hand it over to Maximo, and he'll walk through a project example of a system that Nuvation and Maximo are doing together.
Thank you so much, Michael. That was really nice. Next. Maximo Solar is 12 years company, installation company in Puerto Rico. We do manage storage for over 10 to 15 years. I was doing storage over 20 years ago. And through the experience, we have worked with DC coupling quite consistently. We know the market has moved to AC coupling at some point because of the amount of installation. We foresee that DC coupling is going to be taking over at some point within the next, I would say, less than 5 years. Okay, next slide. I also have a part of the company, Sunbit Energy, which does manufacture lithium-ion batteries and hybrid inverters, and we place them in only one unit. So that's a brand you will at some point hear about. Next slide. So this project is located in Puerto Rico, and as you know, Puerto Rico faced constant hurricane threat. Recently, we were hit by Hurricane Fiona. 2017, we were hit by 2 hurricanes within the same month. So it has accelerated the interest in renewable energy with storage. So this is a 194 kilowatt solar PV array with energy storage. And the requirement from the customer is that we provide 24 hours of backup power to it, to a freezer that has critical equipment during a catastrophic grid failure. Next slide. So the key component of this installation, we have 194 kilowatt of Mission Solar's panels. It is quite important that it's a federal project that require Buy American Act equipment, and that was precisely one of the challenge. You can see that most of the equipment of these companies are USA companies, so this is great to go through the process and understand that USA does have the capability to manufacture high quality equipment and available to DC coupling. So you'll see the EMS and the BMS manufactured by Nuvation, the energy storage battery system by PowerSync. We use an LS bidirectional inverter and the Alencom DC to DC converters. When we talk about DC to DC converters, we hear optimizers, we hear MPPTs for the purpose of this presentation. They're all optimizers or they're all DC to DC converters. And I'll talk a little bit about the difference with charge controllers that has mostly to do when you are charging batteries. Next slide. As with any load, you need to understand precisely what's going to be the consumption. So it was quite interesting to go through the process because the equipment, the load to be served was not built when we initiate the design. So we had to go back and actually do testing and be able to update the design throughout the process. So we just used a regular 3-phase system that was able to load up the information and monitor them for a couple of weeks, and we're able to see the consumption and the peaks of the system. Next slide. And as with any analysis, you have to know how much power are you going to get from the solar array. So we show a PV watt calculation here, but in reality, there's so many software that you can use to calculate energy. So we also work with Aurora and other brands that are out there to design and to understand the power production. Next slide. And of course, understanding the building annual energy consumption, whether this is going to be just a small load or not. The reality is that as you go along the process, the customer might want to add more loads or want to do a little bit of peak shaving, which was the case for this design. So for us to also understand the building loads, it kind of prepared us for that request, and we were able to then adapt the design and make sure that we could meet the customer demands. Next slide. So this is just a graph showing the blue part is the DC battery level. The orange is the energy consumed by the building, and it's pretty much how these charts can explain the availability of solar energy and how can it be used to charge the batteries. And because this is a DC bus, as Michael explains, then the bidirectional inverter can pull power, use the CTs connected to the grid to be able to lower the load without exporting any energy. There's so many things that can be done when you have the DC bus control. You are able to control pretty much all the power. Next slide. And one of the requirements is that the battery never depletes below the 24-hour state. Since we had the load and we know exactly how much power it will consume through 24 hours, the system will be able to add excess power to the building and reduce the building loads, but we will always have a minimum kilowatt hour amount to make sure that the system, if it fails for any reason, if the PV panels get disconnected, if all the building generators are off, you're still going to have at least 24 hours of building power. Next slide. This is a sequence of operation for the grid connected system. So you can see the power sink batteries, the energy management system, the 340 kilowatt hour high voltage battery, and it's connected to the DC bus through the solar array, the all-income optimizers. Like I mentioned before, optimizer in this case are also MPPT maximum power point trackers. In this case, the system is a 1500 volt system, so it's a really high voltage application. And then we have the LS electric inverter, 140 kilowatts. These equipments are great because you can pretty much build the same system modularity and be able to parallel many of these systems and get the design that you want, whether it's 1 megawatt or 1 megawatt, 2 megawatt hour, 1.5 megawatt, 2.5 megawatt hours. It's pretty much the same design. One of the important aspects of this design is that the customer require that in case that the inverter or the system fails, they're able to transfer automatically to the loads of the building, and they're able to continue operation through their generators. So we are able to not only assure the backup power and everything else, but in the event that the 100% of the battery gets depleted, we can still power the loads with the building, and the EMS system from Nuvation is able to know the information and be able to make decision right there. Next slide. Now, what happens when the grid goes off is you have an off-grid system pretty much. The system will continue monitor for power coming back from the grid, but in the meantime, it will be using all that energy to power the loads. In reality, because the load was less than expected from the original design, this system can pretty much operate for over 3 days with batteries. And as we have 4 MPPT optimizer, the all-in-one equipment, it would require all of them to fail or the main disconnect to fail to avoid the PV power to go into the system. So this is a very, very well-designed system. Next slide. Oh, pretty much I'm finished. Thank you.
So with that, I'll provide a little bit of a summary. So as an engineer, we always start with understanding the application requirements and looking what equipment is available that's a match for that application. So to summarize a few points we've covered, DC coupled solar plus storage can provide some advantages such as improved energy efficiency, both for energy storage as well as DC fast charging. It does allow us to do things on the DC bus without impacting the grid interconnect or potentially the grid interconnect permit related to that. So things such as DC fast charging can be added without those sort of permit impacts. There's opportunity to reduce the total number of components in the system. Compare that to the AC coupled side. So the single largest advantage of AC coupled is it is the more common way that systems have traditionally been done. And so there's a larger ecosystems of products and technology, as well as a wider spectrum of domain knowledge as to how these systems are done and to have them work reliably. It is easier to add AC coupled to an already installed system in the field. Adding on the AC coupled level does add to the total AC bus power availability, and so it does give us more flexibility to provide viable solutions for most applications that are out there. So in kind of a summary line, today AC coupled is more common. In our opinion, over time, DC coupled will become increasingly common due to the efficiency advantages and opportunity to reduce component count. So that wraps up our prepared materials. And with that, Maximo and I are available to answer questions.
Yes, thank you both so much. I do see quite a few questions in the Q&A box. And the first one that I'll address, and I know that Missy has also been answering this in the chat, but for all of you that are wondering whether slides will be available, yes, slides will be available. This webinar is also being recorded, so that recording will also be made available after this session's over. It will definitely be on the CESA website, and I believe Nuvation and Maximo will also be able to access that. So diving right into questions. The first question I see here is, will the new Federal Inflation Reduction Act add incentives? I was informed yesterday that there is potentially up to 30% of capital cost incentive available. I can take that one. So the answer is yes, there are definitely significant incentives to install energy storage nationwide, but particularly in California as well. There will be ITCs available for all levels of energy storage, including behind the meter and also in front of the meter. There are some requirements tied to that and some information that has yet to be shared by Treasury or the IRS. So please stay tuned for more information on how to really get that full 30%, including details on domestic content, other requirements. Awesome. Or Michael, Maximo, did you guys have anything to add to that?
I think that's really well said, and glad to see the federal government, supporting energy storage and recognizing that as a distinct part of how we can do good for our planet with our industry.
Yeah. Next question, diving into the nitty-gritty. So when you're designing the rack and container for the batteries, what is the process and timeline to get the product UL 1973 certified?
Sure, so I can answer that. So Nuvation's done this with multiple customers, and there is a multi-step process as to how you do it. So we start with selecting the battery and the battery topology design, and we design the modules and the racking inside of that. That process is, a couple quarters kind of level. And then we go into UL 1973 process. Our battery management system is already recognized under UL 1973, so a lot of the rack level testing is indeed testing the functional safety of the battery management system, and so it's accelerated because we've already completed that process. That then rolls up into UL 9540, which combines your 1973 stack with a UL 1741 PCS. and then you can get a UL 9540 full system. In broad strokes, this overall process of designing an energy storage system with certification is around about a year in terms of calendar time.
Awesome. Well, Leah, I hope that was some helpful insight. One more question.
And whoever asked that question would be happy to talk it through with you.
Definitely. One more question for Michael. Could your EMS be considered an optimizer?
So we can certainly optimize how we're using storage and how we're optimizing the cost of energy. If it's asking optimizer specifically in the context of solar, like we don't do the solar optimizer side of it. So like the maximum power point tracker, that's a pretty tight loop that's certainly in software, but done, in an electrical implementation of the voltage and current that's being drawn. So typically the optimizer loop for solar is built into the maximum power point tracker within the solar equipment.
Awesome. And a question for Maximo. In Maximo's example, does the genset ever charge the battery while the system is on grid, or only in rare circumstances does the battery even get to that low state of charge?
The way the design was handled, we don't need the charging for the generator. We are mostly powering the system. We got so much solar power and enough battery to pretty much be off grid from the system. So although the Nuvation equipment is capable of doing that, in this project we did not include the generator charging.
Okay. And this is a question, I think either of you could answer this question. Are there DC fast chargers that accept DC input, or do we still need 480V three-phase inputs for all of them on the market?
Yeah, there's definitely DC fast chargers that are DC-DC based and can work off of a DC bus for sure. Yeah, it's actually a common application with EV fast chargers to be able to support doing it off a DC bus. Because the DC fast charging is such high power, it can actually significantly add to the cost of a site with demand charges. And so many of these DC fast chargers make much more economical sense to have localized stationary energy storage that slowly charges, and they can do a rapid discharge to charge a car.
Yes.
Awesome. Another question, and what would be the design if we need to use two different types of storage media for the system? For example, lithium ion for short duration storage and hydrogen for long duration storage. Would the battery management system manage two storages? And for Maximo, I'm curious to know whether you've ever thought about these types of considerations or mixing different types of storage technologies.
Well, Nuvation can answer that part, and I'm just gonna say that we have worked different, like wind energy with solar energy. No, we don't have an experience with other, but we have incorporated generators. So as long as they're an AC power source and we're able to control it, I'll let Michael to explain more in detail how it's done.
Sure. So I can chime in definitely on the battery management system side. And so Nuvation's BMS is highly flexible. It works with virtually any chemistry and battery manufacturer. And so we've deployed systems that are lithium, lead acid, zinc, flow batteries, hydrogen, blue Prussian, all over the map. Because for us, we can use the identical BMS hardware, and it's simply loading a different software configuration file in order to support all these different chemistries. And so for us, the BMS is essentially a device driver that abstracts what energy storage is underneath that. Then once it rolls up to the energy management system layer, it's not concerned with what chemistry is underlying that and how the energy is being stored. It just knows what is the available energy, what is the available storage, and what is our charge and discharge current limits. And so that actually works really well. We did a system with NREL Centrica where it was actually 3 different heterogeneous forms of chemical energy storage and batteries. and it was all managed by the identical hardware. So whoever asked that question, we'd love to have a conversation with you as to what you're doing and how our products and services can support you in heterogeneous applications like that.
Awesome. These questions are flowing in and they're really testing my engineering knowledge for sure. So for the DC coupled solution, and I think that this question can be for both of you guys. What are the key differences at the point of interconnection, for example, with protection, if any? So Maximo, are there any differences when you're thinking about Puerto Rico in particular in your guys's, protection requirements? And then Michael, if you know more about different jurisdictions, that would be helpful.
I mean, as long as you stick with the National Electric Code, you'll have protection on the DC side and you'll have protection on the AC side. So, Michael?
Yeah, well answered. In an AC coupled solution, you do need protections per AC connection. So in line with the National Electric Code. Back on that diagram that showed kind of the round trip efficiency, there was a box 42 which represented the grid connection protection circuitry. And you have to do that per AC connection. And so in an AC coupled system, you'll end up with a bit more AC protection circuitry, but also then more redundancy and resiliency. So there's trade-offs inside of that.
Yes, and also in our system, the Nuvation controller is communicating with a South 751 that is connected to a contactor. It will make disconnecting the system as per electrical coding.
Awesome. And Michael, I think you touched on this in your presentation, but someone did ask what the consequences are on transformer design between the AC and DC coupled systems.
Yeah, so in a transformer design, so the transformer is some 99% efficient. And so in a DC coupled system, you don't need any transformers on the DC side. Transformers are just an AC bus component. And it's usually for when you want to go longer distances. And so you might come out of the system 480 volt AC and then want to step it up to higher voltages. And that's where the transformer comes into play. In an AC coupled system, you might actually end up passing through two transformers in order to get to another piece of AC coupled equipment. And so DC coupled, again, offers that advantage of higher efficiency and less components. AC coupled offers higher flexibility. And on the transformer side, you can be further apart in an AC coupled system.
Awesome. For Maximo, in your Puerto Rican microgrid, is the genset ever providing power at the same time as the battery?
Yes, the genset might be providing power to the building, but we will still be providing power from solar energy to the load. So if the generators fails, our battery system will pretty much, this load is totally isolated from the building when the power goes out. It's totally protected by batteries and solar energy system.
Okay. This is an interesting question. In DC coupled storage, don't you think there's an added risk if the PCS fails and consequently both your solar and your storage go down?
Yep, that's quite true. And so that's the trade-off in having a lower component count, is you're trading off some reduction in resiliency and redundancy. So in a DC coupled system, if there's just a single DC to AC converter and that goes offline, then you've lost any ability in order to connect your DC and AC bus together. Now inside of that, you can still continue to operate in your DC bus, but all your AC loads will be down. So that is indeed the trade-off.
Yes, for the system that we have in Puerto Rico, all the MPPT optimizers are and the inverters are separate units, but we understand that for the residential level, there's a lot of products out there that can have the optimizer within the inverters as the technology has changed and we see more transformerless inverters. So allow for more space in the units to carry on the optimizers within the inverters. And yes, that's a real, it's an advantage. What I will say is the rate of failure is so low. The mean time failure of these units are typically over 20 years. So you'll see there's always a potential for something that has some core issues with the manufacturing process, and they will reflect quite fast within the first 30, 60, 90 days. But in the long term, you'll see you'll likely see way less failure when it comes to manufacturing issues versus performance.
Okay. Well, I guess those are some things to consider. Some low probabilities, but
yes,
also potential for failure. I guess that is always the trade-off, right? Another technical question. Based on the projects you've seen, what DC coupling voltages are you thinking will be most prominently used in the future?
So today, you know, a lot of energy storage systems are kind of in the 1,000-volt nominal range, and the industry is going to 1,500 volts. And so new systems are commonly going up to that 1,500-volt range. The higher voltage, you can use less current to achieve the same power being voltage times current. And so if you drop the current in half, because it's an I squared R law on losses, you reduce your losses by 75%. And so we're increasingly seeing both DC and AC coupled systems going to DC stack voltages that are up in the 1,500-volt range.
Yes, I will add to that for the residential system, because of the amount of systems that are installed around below the 500 volts, we have seen that most of the off-grid installation, they run around 48 volts. But we also foresee that there's a lot of manufacturers coming out with a higher voltage system. So it's very likely LG, many other brands out there are coming out with 400 plus battery systems. So it's gonna go up. It's definitely gonna go up.
Okay, good to know. And then, you know, there was a lot of discussion here today about the growing popularity of DC coupling, I think both in microgrids, but also potentially, you know, on the front of the meter side. Why do you guys think that this is the case? Is it because of utility backlogs, which I know that we're seeing here in California for sure, just the efficiency benefits, or equipment availability? Where is that coming from?
All of the above.
The primary thing, go ahead, Maximo.
At least in Puerto Rico, all of the above, but Michael can explain more the situation in his experience.
Yeah, on an engineering level, it's the efficiency is the primary reason. Like, people do energy storage not because it's pretty, but because it makes economic sense. And so the efficiency has a direct impact on the economics of a site making sense. So, you know, we've been doing this for over a decade, and we've gotten DC coupled questions for over a decade. And often when we looked at things, you know, 10 years ago, there just wasn't enough DC coupled equipment for it to make sense. And because there were less options, the equipment was often more expensive because just the manufacturing volume wasn't there yet. So increasingly nowadays, there's more and more DC coupled equipment available, and the costs are becoming more comparable so that it pencils out to make sense. And a lot of these sites are going in for 10, 15, 20, 30 years. And so if the efficiency advantage that you get is in place for decades. And so even if it is a bit more expensive up front, it's the correct move to make from an economic perspective in a lot of these sites.
Yeah. It's a question. Are microgrids being developed? Oh, there are more. They're just flowing in. Are microgrids being developed in the continental US for water treatment and other critical services? I can say that yes, most definitely. You know, there are a lot of governmental agencies that are really interested in having power on site with solar plus storage or even backup generators in order to have power to provide those critical services during outages, and also to provide bill savings, and also to have clean energy. You know, some of our state agencies are really working towards meeting clean energy goals ahead of the entire state. So that's another reason why we really do see critical facilities and government facilities adopting microgrids.
Well said.
Yeah.
Yes.
Oh, this is a good question. From a control standpoint, is AC coupling or DC coupling simpler?
So from a control standpoint, DC coupled offers some advantages that you can set limitations in configuration settings. So for example, you know, charging a battery only from solar power, you know, you can set the equipment to say, you know, never charge this battery from grid connection. You can achieve the same result in an AC coupled system by setting that up inside of the energy management system. So both approaches work. The DC coupled is perhaps simpler in that example.
Okay. And I just realized that we are at the hour, so time flies when you're answering fun questions. But just to wrap it up, I did want to ask if either you, Michael or Maximo, had any final thoughts that you wanted to share with the group.
Yes, another was a question regarding the difference between optimizers and charge controllers. And, you know, basically when you have optimizers, the AC inverter is interacting with the optimizers to you know, disconnect or change the power curve. But when you have a DC bus with the batteries, it's basically the, you know, the charge controller does exactly the same, but now it's looking at the algorithm to charge the batteries and probably disconnect the optimizer when the batteries are full, or provide the power, you know, to the inverter if it's not shaving any energy from the grid or the building loads.
And maybe just in closing, I'll chip in. You know, Nuvation's been doing energy storage systems for, you know, over 14 years now. And when we started doing this, you know, no one understood what energy storage was. I would mention it at parties or try and describe to my friends, and people don't understand. And now it's very mainstream news.
Yes.
And you know, we host webinars and 600 people show up, which is awesome. Thank you for being here. It's just such an honor to be involved with an industry where we can run successful businesses and make money, and also do things that are good for the planet. So it's very fulfilling for us at Nuvation that our products and services are things that are, you know, helping reverse climate change and taking care of this planet that we all live on. So thank you for that.
Those are great words to leave off on. Thank you, Maximo. Thank you, Michael, for joining us today. I personally learned a lot. I hope everyone here did. And if anyone has follow-up questions, I know that there are a lot of questions in the Q&A that we weren't able to get to, so thank you all for your questions. But please feel free to email any of us. Michael, and Maximo's contact information is there on the slide, so we do look forward to hearing from you, and thank you all for joining today.
Great. Thank you, Grace. Thank you, Maximo.
Thank you.